It's really encouraging from a climate scientist perspective to look into the audience and actually see quite a few faces I recognise. That's encouraging because it means we are actually starting to talk to each other. What I want to do today is really come up with two things. So one, I want to give an impression of how the climate might change over coming decades, but I also want to try to answer the question, what can climate science do for you? So I'll home in on some of the tools we have available and how they might be used to, for instance, feed into stress testing and feed into some of the other requirements you have for environmental information. So the starting point for any talk like this is really observations. Observations are essential if we're going to understand present-day hazard and risk. And what I'm showing here on the left is an infographic we prepared for the UK looking at changes in climate extremes. So just picking up a couple of those, you can see, for instance, that if we compare the period 1961 to 90 with a very recent decade, we're seeing increases in the hottest day of the year of nearly a degree. We're seeing increases in warm spells, almost doubling in length over that period. We're also seeing increases in the coldest day of the year. And you start to see quickly, well, okay, the situation's a bit complex here. We're seeing, for instance, the winter warming more than the summer. So there's a seasonal pattern to some of these observations. If we focus on rainfall, then we can see that the longest dry spells have decreased over this same period. But when we look at the most intense rainfall events, there's actually more rainfall in those very heavy events that typically lead to flash flooding and issues around urban drainage. So we've seen changes in extremes of various types. Alongside these atmospheric extremes, we can also go out and measure changes in sea level rise at the coast. Now that's both mean sea level, but also if we want to look at coastal extremes associated with storm surges. If you want to use observational data, it's actually now very widely available. And it'd be interesting to debate whether it's in formats and forms that you can use and that are accessible. But the plot on the left, this is drawn from the National Climate Information Centre. And from here, you can download gridded data. We now have, for instance, temperature and rainfall data with records going back more than 100 years, and some of that data on kilometre scales. If you look on the right, what I want to illustrate there is we also have a number of global records. When we look globally, the coverage tends to be less complete. Some parts of the globe are much better covered than others. But as we move forward towards the present day, and certainly into the satellite era, we find those records are becoming more complete. And the raw data is available, but then so also is the processed data. So data that has been quality controlled. And increasingly, there are digested forms of this. So I'm showing here the bulletin of the American Meteorological Society's annual update on the state of the climate. And here, there's a focus that goes all the way now from what's happening in atmospheric composition through to the weather on quite a local scale. So it would be great if we could do everything with observations, but of course we can't. And we can't because we're in a changing climate. So actually, the observational record is quite short if you want to look at rare events. Looking at the past events is essential, but it's simply not sufficient. And if we look at aspects such as the National Flood Resilience Review, it becomes quickly clear that there could have been extreme weather events that we're simply not picking up in the short observational record. So how can we deal with that? If we're trying to understand the present, then I think one of the exciting new approaches is shown on the left, the so-called unseen method. And what we do there is we use the same type of weather or climate model, same type of weather model, we look for the forecast a few hours or a few days ahead, and the same type of climate model, we look years into the future. And we say, can we use it in a slightly different way? So if we use something called initialized forecasts, and this is where we try and pull the model state back to the observations and then run it forward to track the natural variability in the atmosphere and ocean. Traditionally, we haven't just started at present day, we've gone back in time and said, well, we want to make sure the system works, so we perform hindcasts with that. And that was always a very important evaluation, a very important validation task. It gave confidence in the modelling system. But what we realised is all those hindcasts that we were kind of just pushing to one side when we checked the model was okay, are really useful. They're providing a synthetic view of the recent past, but one that is physically consistent. So it's not simply a statistical extrapolation. It's preserving our understanding of the laws of physics that govern how the atmosphere works, and it's preserving the relationship between different metrics like temperature and rainfall. And doing that, we can build up a really large set of what the atmosphere might have done in the recent past. So for instance, to give a feel what that might tell us, if we were to look at rainfall records in the southeast of England, the first study using this suggested actually, if you take any winter month, there's around a 7% chance of beating the observed record. If you look over England and Wales as a whole, there's about a 33% chance. And so it's letting us push further into the tail of these very rare events. On the right is another approach. It's called event attribution. And what we're trying to do there is understand what has caused the types of events we're seeing. So it's possible to take an observed, for instance, high temperature event like summer of 2018 or an extreme month of rainfall and say, well, if we look at the odds of this happening and compare it to a world in which there were no increases in human-driven greenhouse gases, what would be the difference? And doing that, we can tease out the fingerprint of human activity. It also gives us another estimate of looking at the present-day risks alongside the unseen method. So the sort of statement we might produce is, an example here, 90% confidence that we find man-made forcings have increased the chances of record warm years in the central England record by a factor of 13. So it's giving us that extra piece of information. We could also say, well, in the present day, this gives us the statistics, but do we have any ability for early warning beyond the few days to a few weeks ahead one can get from a weather forecasting approach? And here we're seeing the same initialized forecasts that we've used in the unseen method. When we run those forward in time, we can latch on to the variability of the real atmosphere. And what you're seeing on the left is it's a particular metric from the atmosphere, the North Atlantic Oscillation Index, basically a measure of circulation over the Atlantic and Europe. And the black line is showing the observations, and the red line is showing the model. And what we're finding now with seasonal forecasts is we have skill when we're looking in winter months of the order of a few months ahead. And actually, we're finding users telling us this is useful skill, for instance, if they're thinking about energy planning needs a few months ahead. There have been two major steps forward in this over the past couple of years. One of them is to push further into the future, and actually, there's useful skill even into the second winter, and that opens up a whole new set of potential applications. There's also skill that can be teased out over the summer months, and this was an area where people previously said, well, okay, this technique's good for winter, but not for the summer. So it's possible, alongside the statistical assessments of what a present-day climate might look like, to actually try to track the state forward in time and comment on whether we're more likely to get a wetter or a warmer or a colder or a drier winter. So that takes us a little way into the future. A question that really interests me is, what if we want to look further? And what does the world look like if we look several decades ahead into the future? So what I'm showing here are the most recent reports from the Intergovernmental Panel on Climate Change. So the bottom left is their last major assessment report, so-called fifth assessment report. And a lot of people still use the data from that. It can be downloaded, it's freely available. Since then, there have been 3 special reports, which you can see on the top level, and the data for those is also available. I'm also showing on the bottom right a project that it's focused on the UK. It was funded by Bayes and DEFRA to produce a new set of UK climate scenarios. And what we did there, we produced a set of different tools. So if you start at 11 o'clock, we produced a set of probabilistic estimates of the range of future changes we might expect over the UK out to the end of the century. But then increasingly people were saying, well, that's great to have a PDF and use that as a way of combining information, but it would be great to have some realizations of that. So we used the newest climate model we have, which we know is much better at simulating synoptic variability, the weather over this region, to produce global simulations. And we accompany the PDFs with 28 additional simulations of how the world might evolve. That's at a detail of 60 kilometers. But a lot of people are interested in extremes. And so we downscaled that over Europe to 12 kilometers. And that gives us a way of looking in more detail at many different types of extremes. And what we've done most recently, that I think is just incredibly exciting, is to take the very high resolution weather forecast models, the sort that predict if there's going to be an intense storm over your part of the country. And these run at a scale of 1 or 2 kilometers. And traditionally, they've only been run out a few days ahead. And we took one of these and we produced 12 different versions and ran it out to 2080. And so we've got this new, very rich set of information that covers the UK. Alongside that, we also produced a set of marine scenarios, so updating the estimates of sea level rise around the UK and accompanying that with estimates of change in storm surge and waves. So there's a lot of data out there. The trick is then starting to interpret it and use it in a useful way. So I'm going to go through, very briefly, a story of starting at the global scale and then homing in to the UK scale. If we want to make projections of future climate, decades into the future, then the starting point is, for climate, is to have some emissions. We need to have scenarios of what those emissions might be. Those are produced using integrated assessment models. The assessment models consider things such as, well, the scenarios are what will the population be like? What will world GDP be like? What will trade be like? What energy technologies will be available to us? What can we assume around technologies for demand? And from those integrated assessment models, it's possible to construct a whole set of outputs, including emissions. And in the IPCC 1.5 degree report, they were able to compile around 400 different scenarios from quite a large set of different integrated assessment models. And that's really important because it captures the structural uncertainty that is inherent across the models. Any one model on its own, I think one has to use with extreme caution. So the plot on the left, the grey line, the grey range, is showing the range of CO2 equivalent emissions when we look across 411 of those scenarios. Actually 410, because there was one we had to throw away. The plot on the right is showing the global average warming response relative to pre-industrial levels. So you can see in terms of warming, there's a very large range, going from, like you can see, of the order in 2100 of around a degree, up to off the scale, so it goes up to 8, 9 degrees. The yellow band is the band that passes through the NDCs, the pledges of emissions in 2030, including the uncertainty range. And you can see, well, already that's narrowing the range of temperature outcomes. And we said, well, okay, if we take these, can we go a little bit further and say, which scenario passes through the pledges of emission reductions and gives us the lowest temperature? That's the red curve. So the red curve, it just passes through the bottoms of the pledges on the emissions curve, and you see if you look on the other side, it's peaking a little bit over 1.5, maybe about 1.7, and then coming down towards 1.5 at the end of the century. But there are scenarios in the data set that peak earlier, that lower emissions more rapidly, such as the blue curve. That was the one we found with the lowest peak warming, and that peaks the warming below 1.5 degrees. So that's a starting point, and if you're interested in physical risks, that's giving you a global average, annual average temperature. But nobody lives in the global average, and nobody lives in the annual average. So how do we increase the richness of that data? Let's give that one. Of the 400 scenarios, while we can run all of those with a simple climate model, the really complex three-dimensional climate models that are based on weather forecast models, we can only really afford to run those for a small subset. So typically, in the past, we've run them for of the order of 4 of the scenarios. There'll be slightly more in the next IPCC analysis, but it's very much a subset in an attempt to cover the range of forcing. So how you link those complex 3D model scenarios to the larger set of 400 storylines, I think is an area for quite a long debate. When we look in the complex climate models, we'll see plots like this. So the temperature's on the right, the rainfall's on the left. And this is the increase from near present day out to the end of the century. And you can see in the high scenario, we're getting temperature increases up to about 4.5 or 5 degrees over many land areas. In the poles, we're getting an even greater increase. If we look at rainfall, then we're seeing a mix of areas that are drying and areas that are becoming wetter. So typically that contrast that we see in present-day climate between wet and dry tends to increase. If we want to zoom in, we can do so over the UK. And what I'm showing here is an output from UKCP. And all the areas over the UK are expected to warm, but the future rise, as you might expect, depends on the emissions. The lowest scenario is compatible with 2 degrees that we looked at, but the highest scenario takes us much further than that. And these temperature maps are showing by 2070 the increase in the high emission scenario. So you can see a gradient of temperature over the country, and you can see increases in the south of the order of 5 to 6 degrees. Again, there's a seasonal split, and now if you look in summer, you'll see slightly higher rises, in winter slightly lower rises, for reasons we physically understand. We can also look at the change in probability of extreme events. So we could say, summer like 2018, what was the probability of that? So if we go back to our baseline period around 1990, it was less than 5% to see a summer like that. By 2018, that had risen, depending on how you calculate it, to somewhere between about 10 and 25%. But by the middle of the century, we give a 50% chance of that type of summer occurring. You can start to see the difference between the low and the high emission scenarios, but it really only becomes great towards the end of the century. So we can interrogate the climate models in this way. We can also look at rainfall change over the UK, and now I've taken the same emission scenario, so still looking around the 2070s, and you can see in the summer we're getting reductions that go down to, in a central case, of the order of 25 or 30% reductions in rainfall. And in winter, going up to 25 or 30%. When we take the uncertainty range into account, those changes may be considerably larger than that. And you can see some reductions on the left-hand side getting down to in excess of 70%. So we're talking really large changes. We also see in the new simulations with the very high resolution model, the 2.2 kilometre model, that when we look in the summer, we get this interesting situation that the seasonal average decreases, but when it does rain, it tends to rain in much heavier amounts, so it's a greater intensity. So you can imagine a situation of having to deal with flash flooding, but also drought at the same time when you look on the seasonal scale. Sea level rise is predicted to increase in all of the scenarios, and even in the 1.5 degree world, sea level rise will continue after 2100, and it will continue after 2200 and after 2300. There's a very long time scale associated with sea level rise. You do see benefits from mitigation, and those benefits accrue over time, but by 2100, the benefits may only be a few centimetres. There'll also be changes in storm surge and tidal characteristics, as well as sea surface waves. In terms of the numbers, well, these are the relative sea level changes. And if we take somewhere like London, in the low scenario, we're seeing a change from about 30 to 70 centimetres, and in the high scenario, going up to around 115 centimetres by the end of the century. It's slightly lower in the north of the country, and that's due to the vertical movement of the land. So my final slide is to illustrate one of the things that we are much less certain of, and that's the idea of thresholds or tipping points in the climate system. This is based on a plot from a famous paper in 2009 by Kriegler et al. And what they did was highlight, well, not only are there thresholds either of irreversibility, like the melting of the Greenland or the Antarctic ice sheets, or abrupt changes, such as changes in the Atlantic overturning circulation, but there may be links between these system thresholds. And we're only really just getting to the point where we can start to model some of those links. So putting numbers on them is incredibly difficult. And what that means is, while we can produce a range around some quantities like temperature or rainfall, there are additional deep uncertainties that the subject is still really trying to explore. So I think that's probably a suitable place to stop the climate science introduction. So thank you. So I think understanding of the individual components of the system has been increasing over the last 10 years or so. So there are processes such as how ice cliffs form and contribute to collapse and possible acceleration of the ice sheet deglaciation and disintegration. There has been steps forward around aspects of permafrost thawing. The coupling of them, I think we're just getting to that point. So we finally, in the next IPCC report, and the simulations for that are literally running as we speak, we finally have access to the models that allow us to look at some of those interactions. So the interactions, for instance, I don't need to go back. The interactions, for instance, involving permafrost and its amplification on warming, I think we can now get a better handle on this time around. I think some of the impacts of fresh water on the overturning circulation, I think we can get a better understanding of. And some of the tropical circulation changes, again, I think the models have improved sufficiently, in that case, because of their spatial detail in the tropical region, to enable us to really start to build our understanding. And then I think the next phase is saying, well, okay, our understanding gives us a wide uncertainty. What can we do to constrain that uncertainty? And I think that's what we'll see happening over the next 10, 15 years in this subject.
Do you think that the way scientists talking in terms of uncertainty, I understand why you do that,
Yeah.
But it kind of rather makes people think, oh, it's all uncertain, so let's not bother. And how do you think you might change your language to say, well, actually, we're pretty certain, it is going to happen, it's just we don't know exactly how? Because I think that might help.
I mean, I think this depends on the audience as well to some extent. And this is something we debate a massive amount in the community, a massive amount in the Met Office. So typically we actually start a tale like this with the observations because we can say what has happened. By linking it to things that people are much more familiar with in the real world, in their everyday lives, I think gives us a route into it. The uncertainty question, I think there are two things that occur to me on that. So one of them, often we talk about the range of future warming. So rather than talking about the uncertainty in future warming, we will say, using our models for this estimate of emission, we can, using our knowledge, come up with this as a likely range. And so words like likely range, I think, help with that. I think one piece of advice a colleague gave me who'd spent a long time working in aspects such as international security, he said, well, tell them what you know, tell them what you think you know, and then tell them later what you don't know. And I think there's some help in that as well. There's also the approach of using analogues, and I think this idea of being able to root future projections in terms of past events and what we expect to happen to those based on the fact that this is all built from the laws of physics is part of the story. But advice is also very welcome from the different communities we talk to. What do you think?
I think it's really difficult. I mean, my background's as an economist, and I feel slightly guilty because I think I ignored the environment for most of my life. And I think that's partly why we're in the mess we're in, actually, that we haven't priced these externalities or really thought about the sustainability of our development. So, and I find working with financial firms now on the risk management side, they don't even know where to start to think about this stuff, and it's quite difficult unless, it helps when the regulator, frankly, tells them they need to think about it, because then they go, okay, right, I'm going to think about it. And then once they start the journey, they reach a tipping point where they think, my goodness, this is quite profound. We really have got to get on with it. But until they reach that point, they don't think it's relevant to them. And it's only when they're kind of forced to think about it. And I suppose what I crave is almost like, I don't know whether it's a primer or something that you've produced, which just goes, look, you've got to read this, that, everybody has to read this. And then, let's have a discussion about how you can move beyond that tipping point to actually doing something about it. But there's a bit of a disconnect, I'll be honest. Most people in financial services just think about the next quarter's earnings, and they don't think, and not all of them, but an alarming number of them do, and they haven't got to that point where they've even got the basic understanding.
I mean, I suspect to some extent the opportunity there is to get people very early in their career. One thing my team has done very recently actually has been to contribute some of the climate information into training material for the finance sector in an attempt to do that. And I think it's that sort of getting in at the educational level. It's probably going to take a generation to change, but the long term, ideally we have people who are more environmentally literate as well as economically literate.
I agree, it's just, I think we don't have that.
No, that's the trouble. That's the challenge.
Building on a couple of the points from the previous question, that aspect of time horizons for the projections, I don't know, with respect to business decision making, 10 years is a long time, so 2030, 2050. I wonder if you've got any thoughts on reporting climate projection and impact work over those sorts of horizons. Also on the climate scenarios that you mentioned, the 400 from the integrated assessment models, ideally, again, echoing some of the aspects for consistency of reporting from this morning, to what extent can we look towards sort of ad hoc de facto standards coming out of some of that work? And on the uncertainty question, perhaps the other way around as well, one can start to see emerging commercial startups, for example, with climate solutions that don't seem to have any uncertainty at all in some of their prognostications and work. It would be great if the Met Office perhaps could shine a light on some of that work from a transparency perspective.
Yeah, so thank you. That's a lot of questions there, John. I should say John and I have a number of these discussions that go on quite a lot, so I do welcome the questions. I think the time horizon is a really difficult one. And the time horizon, it's so difficult because when you're looking on very fine spatial scales and you try and project forward, it's difficult to tease out that long-term signal from the background variability. So I think the two things that typically we try and do there is, one of them is this focus around, can we say more about the statistics of the present day? And the work I showed on the unseen approach is starting now to pull through to impacts calculation. So where previously we'd focused it on what does it mean for temperature, we're starting to ask the question in, well, can we say something about something that's closer to an impact on a person or a business? I think the initialized forecasts, because they are showing skill, there is the possibility of bringing in impacts there. But what we have tended to do is try to work with people who might want to use those, who understand their vulnerability better. So for instance, we've done some work with the transport sector and DFT to understand how they might factor that knowledge on whether statistically the coming winter might be slightly wetter or slightly drier or slightly warmer or slightly colder. So I think it's starting to pull into impacts, but via the individual users. And to me, that's the right way of doing it, because the individual users understand their vulnerabilities much better than we do as climate scientists. The standards question. I mean, there's probably a lot of people in this room better placed to comment on that. But I personally see the standards and the uncertainty, or certainty, whichever way around we want to phrase it, very closely coupled. And I can think of examples where people have tried to simplify the climate information, and in doing so, they have missed out futures that certainly are physically possible and may have a very high impact, a sort of high plus plus type events or black swan type of events. So I think in developing the standards, it's necessary to appreciate what's going into them, all the way from the integrated assessment models and understanding just how limited any individual model can be. But by using the collection of models, you can learn something extra about what's happening. Well, it's the same with the climate models. You have to understand physically that range that's coming from the models, what it means and how robust it is. And one of the areas that I think is related to standards is trying to accompany the projections of the future with narratives of how physically robust and how credible each of the scenarios are, based, for instance, on that understanding of the physics. And you could imagine a narrative that goes all the way through the choice of socioeconomic assumptions, the choice of integrated assessment model, through the choice of climate projection, that gives you that extra information, that gives you more confidence in a standard.